Yep. Welcome everyone to the One World Mind seminar for Thursday, March 14th. It's our pleasure to have Kevin O'Neill here today to speak to us about sketching the heat kernel. I'll let you take it away.
Well, thank you for the introduction, and thank you to the organizers for the invite. So the starting point to this is a motivation that you see in a lot of places. We have data which is in very high dimensions, but there's some sort of inherent lower dimensional structure to it, whether it be on a manifold or just something else. And so we want to take that data, we want to embed it in much lower dimensions where we can analyze things more easily. So for instance, if you want to run a clustering algorithm, those may run faster in lower dimensions. Okay. And you can do a similar thing with data from graphs too. We're just getting any sort of Euclidean structure could be helpful. Okay. So we won't spend too much more time on that general motivation that you've probably seen before. But here's kind of a brief outline of the talk. So first, I'm going to tell you what these Gaussian process embeddings are. And then in order to understand some of their key properties, we're going to have to take a detour and talk about diffusion maps and diffusion distances. Then we'll see how the two are connected. And then I'll show you some experiments that we ran for Gaussian process embeddings to show how they work in practice. So what is a Gaussian process? Well, it's a random real-valued function on some parameter set we call t. And if you look at any single value of t, then and you look at the distribution of the function evaluated at that point, it's going to be a normal distribution. Okay? So you can think of this as a multivariate Gaussian, except there's going to be some sort of underlying structure to the parameter set t that's going to be valuable whenever we discuss these. So the t could be a manifold, it could be a metric space, or it could be just an interval or the real line, which is what motivated the term Gaussian process to begin with. So if you have a Gaussian process or any multivariate Gaussian, it's uniquely determined by its covariance function. This is going to be a symmetric positive semi-definite function, which we computed with this formula. All right, so if you have a Gaussian process, it also gives you a pseudometric, okay? So what you do is you just look at the expected square distance between 2 points. When you evaluate your function at those points, you take the square root, so it normalizes, and that's a distance. So it is a pseudometric officially because it could be 0, even if the s and t are different points. But you can think of it as a metric. Okay. All right, and if t is discrete, then C is just a symmetric positive semi-definite matrix. Okay, so we can talk about things in the more abstract continuous setting. But then eventually we're going to discretize everything. So I'll be trying to make sure everyone's up to date on what the discretizations look like as we go. Okay, so how do we use these to make embeddings? Well, we're given a Riemannian manifold and a metric G on it. And we want to not just take any Gaussian process, we want to take one that's consistent with that metric. Okay, so here's a fancy formula which describes this relation. It says that if you take any two directions in the tangent space, and you take the derivatives of the covariance function with respect to those directions at a particular point, then you should recover what the metric tells you about those directions. So if you're familiar with Riemannian metrics, great. If not, you can just think about taking the covariance function to be any sort of isotropic kernel. Okay, you can just imagine some subset already embedded in Rn, and just look at the covariance of some function of the distances. Okay. So here's what the Gaussian process embedding looks like. What you do is you assign k, we're going to Rk, so you have k different coordinates, and each of those coordinates is an independent realization of the Gaussian process. Okay. So these are all realizations of f, and then we normalize divided by the square root of k. So the basic idea here is that if you have 2 points which are originally close in your manifold or in your data set, then they're going to have a very high covariance. And so you expect f of x and f of y to be close for any realization f of your Gaussian process. Okay. So this kernel k is going to be perhaps 1 when the input here is 0, distance 0, and then it's going to decay to 0 as these points move further away from each other. All right, so that's just kind of a very crude kind of why this might be plausible. There has been some work done on this before in a more theoretical setting. Okay? So what we knew going into this was that these Gaussian process embeddings are almost surely embeddings, provided you embed into a high enough dimension. Okay, so if this lowercase d here is the dimension of some manifold you have, so let's say you have a torus that's two-dimensional and you embed into R5 or higher dimensions, then you're going to get an embedding. You're not going to have any self-intersections. Okay. All right, so this model is actually introduced in this paper from 2017. And the point of it was just to have some sort of model for a random manifold. Okay, what does it mean or an arbitrary manifold in a sense? And so what they did was they showed that if you use this embedding on a manifold and you embed into higher and higher dimensions, then the reach of this embedding converges to a non-zero constant. Okay, so what is a reach? You haven't seen this before. What the reach is it represents a couple things about a manifold. So here's a manifold in blue. And if you take some point which is very close to the manifold, where my cursor is now, then in a neighborhood of that point, the manifold is going to look a lot like a linear subspace. And so it's going to have unique closest points to my cursor, right here. As you move further away, eventually you get to a point, so this is a circle, this would be the center of the circle, where there's more than one closest point to my cursor. And so then that distance from the manifold is the reach. It's the smallest such distance. So this is a very large reach. You have to go far from the manifold to get this to happen. This is a very small reach. If you just go a small distance, you can see that these are equidistant. But you can also get small reach, not by having large curvature, but by having the manifold kind of turn around and get close to itself after winding around a lot. So this one is supposed to have a very large curvature, but still a very small reach because these two pieces get very close. Okay. So what they showed is that essentially when you take manifolds of very high dimensions, that the reach is not a problem. You're not going to get these near self-intersections. Okay, so I wanted to describe that a little bit because I think it's an interesting result and because it was the first place where this came up. But the result that's a little more relevant for our work today is a follow paper by them where they showed that the pullback metric, that is the distances that you have in the embedding, essentially, they converge to the original metric as you embed in higher dimensions. Okay. So that is a nice quantitative result that tells us it's a little better than just the simple, if 2 points are close initially, then they should be close in the embedding. Okay, so what we did was we discretized this. We said, what if we have actual specific data, no kind of analytic formula? What happens when we do these Gaussian processes embeddings? Okay, so how does that work? Well, we pick a symmetric positive semi-definite matrix A to serve as our covariance matrix. And maybe that's the affinity matrix for some isotropic kernel. And then we just have to compute Gaussian processes that have that matrix A as the covariance matrix. Okay, and then you just do that k times, you use those coordinates, and that's it. Okay, so how do we do that? So you may have seen in a math and data science course or whatever, or statistics class, that if you have some sort of random variable which has a covariance matrix which is not the identity, and you multiply by the inverse square root of that, then you end up with something which is just your standard multivariate Gaussian. So conversely, if you start with your standard multivariate Gaussian, and you multiply it by the square root of the covariance matrix that you want, you end up with a multivariate Gaussian with that covariance matrix. So we're going to use that here. We're going to have some data. We're going to construct some sort of affinity matrix. Then we're going to compute the square root. We'll hold off on that for just a little bit. And then we have to multiply by a bunch of IID Gaussian vectors. Okay, so that amounts to If you want to do multiple of them, it's just multiplying by a matrix of IID Gaussians. Okay, so this is your standard sketching the matrix. It's a very, very simple thing. People do it all the time. Okay, you take the rows of the sketching as coordinates for your points in RK, and you're done. All right, so what is the best way to compute the square root of a matrix? So sometimes people use, okay, so first the square root exists. We have a nice positive semi-definite kernel, positive semi-definite matrix. It's going to have a unique square root where you diagonalize it, you take the square root of all the positive eigenvalues or non-negative eigenvalues. But instead of doing that, you might maybe use a Cholesky decomposition. I gave another version of this talk before where somebody pointed out a version that's a method that's iterative and converges after many steps and is more efficient for very large matrices. But nothing beats already knowing the answer. So we're going to modify this algorithm. We're going to fix our matrix A, and then we're going to say, well, you know what, A squared is also symmetric, positive, and semi-definite. It's going to have the same eigenvectors, very similarly behaving eigenvalues. And so we're just going to compute the Gaussian process with covariance matrix A squared. So no taking the square roots, just use a slightly different covariance matrix. It's something arbitrary, just going to have certain nice properties. We'll save ourselves some time, have a really quick algorithm. Okay, so this is the actual one. Construct your matrix and sketch it. Okay. So, all right, so a quick, just kind of mini quiz, not that you have to, not that you have to be able to figure this out necessarily, but to kind of make sure we're comfortable with some of the basic ideas and to see something we'll actually use later. Let's say we have this Gaussian process with the covariance matrix A squared, and we want to know what the corresponding pseudometric is between two different points. Okay. So what we would do is we would look at the Gaussian process that you generate by taking the matrix A and multiplying it by an ID Gaussian vector. And then you just have to kind of expand your squares, and you end up getting just the L2 norm of the difference of the rows of A. The ith row and the jth row corresponding to these points xi and xj. It just follows from the simple fact that you've probably seen before about expected values of ID Gaussians dot product certain vectors. Okay. All right. So what do we know so far? We have these Gaussian process embeddings. They should be embeddings. We haven't proven that for any discretization yet, but at least in the theoretical continuous realm, these are going to almost surely be embeddings. We know they preserve local distances at some level. It should be relatively easy to compute. We just have to sketch a matrix. That's pretty simple. Though we haven't talked about how to get that matrix to begin with exactly. And also, for every time you have an embedding, it's associated with one of these matrices and a pseudometric. Okay, there's two objects that are attached. Okay, so what do we not know? Again, we don't know how to choose this matrix A. There's a reason I'm holding off on this. We don't know how good these work when they're discretized. What can we actually prove about what happens when we discretize? We're not going to have this continuous Riemannian metric anymore. And also, how do these relate to other embedding methods? We can say, okay, it's good. Maybe we can prove that in some limits, we're going to get some convergence to a distance. But if it works more poorly than every other method out there, that's not a good thing. So that's where we need to go. But in order to get there, we have to talk about diffusion maps. Okay? And it won't be clear immediately why, but they're going to be connected. Okay, so what are diffusion maps? So you have a positive definite kernel, which is also symmetric, on some space. And what you do is you turn it into a Markov chain. Okay. All right, so I'm using this kind of abstract terminology with some measure space to do this in the most generalities possible. But you can think about this as just a x is a discrete set, and then mu is just going to be the counting measure, if you like. Okay. And in that case, what this is you're basically taking the row sums of your matrix, and then you're dividing each entry by the corresponding row sum to row normalize. So you get a nice Markov chain. And that Markov chain is going to have some kernel p, lowercase p And then we can think of the operator as capital P. All right, so what is the purpose of this? Why would you care for analyzing data? So what we have over here is you have 3 different Gaussian point clouds all embedded in R2. And you can imagine taking a point mass and putting it at one of the points in this point cloud. So you have it there, and you can do that as some vector, which is 1 in one position, 0 everywhere else, or a function on all these points. And what you're going to do is you're going to take that vector and you're going to multiply it by the transition matrix for this Markov chain. And what it's going to do then is it's going to send some of that mass at your starting point to nearby points. And you do it again, it's going to send that mass a little bit further out to other nearby points, and again, and again, and again. And when you get to 8 steps, it may look something like this, provided you choose your initial kernel properly. Okay? And what you can see is that the mass is spread everywhere to this point cloud, but not to the other point clouds. Now, you run this just a little bit further in time, and what's going to happen is the mass is going to jump from this point cloud to this point cloud. And once it gets over here, it's going to spread around this point cloud and eventually reach some sort of almost equilibrium where it's fairly evenly distributed among these 2 point clouds and not in this one, which is a little bit further away. Then if you go way, way ahead in the future, you can eventually get to the 3rd point cloud. So why is this valuable? Well, what it does is it tells you something about the clusters here. If you look at this with your eyes, you can see 3 different point cloud clusters. If you just look at Euclidean distances, you would say the distance between here and, sorry. It's not trying to highlight that. Sorry, this between this point here and this point here is the same Euclidean distance as this point and this point. Yet somehow this point clearly belongs to this cluster instead of this one. Okay. So diffusion helps us measure that. Okay. Now on the right here is the corresponding transition matrix taken to the appropriate power. So you take it to low powers, then what's going to happen is anything that corresponds to this point cloud corresponding to this block is going to go to itself. Anything in this point cloud is going to go to itself, or something else in the same point cloud. You have this kind of block structure to the matrix. Okay? And eventually you get something which is all kind of uniform. Okay, so that's what this diffusion process is for. I should also say, I should give credit. This is from the original diffusion mass paper. This figure right here. Okay, so we have a Markov chain. It has a nice stationary distribution. You can show that it has eigenvectors and eigenvalues. And we're going to now define a diffusion distance. Okay? And the diffusion distance is going to depend on the time as well as the 2 entry points. Okay? So the way it depends is that if you look at a very short time period, you're going to look at, well, whatever time period you have, you're going to look at the transition kernel for that amount of time going forward. And you're going to compare those 2 kernels. And you're going to take this kind of L2 norm for the 2 kernels. Okay? So if you want to know how close X and Y are, you look at not the distance between X and Y, how long it takes to diffuse from one to the other, but you look at all the points in your set and compare how long it takes to diffuse from X to that point and from Y to that point, in a sense. And then you just kind of normalize, and you get this nice expression in terms of the eigenvectors and the eigenvalues. Right. So what this diffusion distance does, it reflects the connectivity of your data set, kind of think of it as a graph. And yeah, it's a very valuable tool. It helps quantify what we saw in this figure over here. Okay. We're also going to ignore, so eigenfunctions here in x from 0, here in x from 1. The first eigenfunction is just identically 1, so we're going to ignore it for purposes of computing distances. Okay, so diffusion maps now. We have some data, and we're going to embed it in RK, and we're going to use the eigenfunctions as coordinates, and we're going to weigh them according to the eigenvalues. So then what happens is, if we measure the straight line distance in the embedding, so look where one point goes, another point goes, and we measure that, that is not exactly the diffusion distance. The diffusion distance, if we go back here, is the sum all the way up to infinity, or however far you can go if you have a finite set. This is truncated at some level k. for eigenvectors. Okay. And what this does is in some ways it makes the best approximation possible because you're taking the ones that have the highest weighted eigenvalues. These eigenvalues are decreasing. Okay. So this embedding is very helpful if you want to compute all the diffusion distances up to some level. Okay. All right. So if you can do diffusion just with whatever kernel you want. Sometimes you care about having in particular the heat kernel on a manifold. Okay, so if you do that, you can do this kind of fancy normalization process where you basically adjust according to the sampling density. You normalize according to that. Then you do the exact same thing we did before. You get a new kind of Markov chain P epsilon, and you take high powers of that, you approximate the heat kernel on the manifold. Okay. So this is also valuable in that sense. It's not just kind of, you can do it for arbitrary diffusion, but you also recover a very particular and important Markov chain in the heat kernel. Okay, so before we go any further, I want to just kind of give one extra motivation for diffusion maps that I think has kind of been underappreciated, but in some ways fits the same spirit of how we're motivated for our Gaussian process embeddings. Okay. So here's the setup. So we're going to assume we have a manifold now. So nice and compact. It has a Laplace Beltrami operator, and it has corresponding eigenfunctions and eigenvalues. And from that, you can define a heat kernel. At any given time, it's going to have the same eigenfunctions, and the eigenvalue is just going to be e to the minus the Laplacian eigenvalues times t. So what this theorem says is that if you do something that looks a lot like diffusion maps, then you get an embedding, and the metric in the embedding is going to converge to the original metric on your manifold. Okay, so what is this? So ignore everything here, which is just constant, just normalization. Here you just have eigenfunctions and the eigenvalues of the heat kernel, which is exactly what we were doing for diffusion maps. It just goes to infinity because this is a nice theoretical result. And what it says is that the metric that we were talking about, this diffusion metric, if you zoom in really close, make it a Riemannian metric, and you let t go to 0, then yeah, you're approximating the distances to your original manifold as well as you'd like. Okay, so as an example, which is much simpler than all of this theory here, if you have the circle S1, you could look at its top eigenfunctions for the heat kernel. Equivalently, its lowest eigenfunctions for the Laplacian. They're 1, sine theta, cosine theta, and so on. And so if you do this diffusion maps embedding, what you're doing is you're ignoring the one. This doesn't distinguish points. But you look at sine theta and cosine theta, and you get this nice perfect parameterization of a circle. Okay, so there's still a little more left to go in order to fully compute the diffusion distance, but you already have a very nice embedding. Okay, so let's go back to the Gaussian process embeddings. That's actually maybe that's a good time to pause it just if there's any questions before moving on to the next step. Okay, fine, that's fine. Well, let's continue. Okay, so let's go back to Gaussian processes. So Gaussian process covariance function. This is an important result called the Karhunen-Loève expansion. And what it says is that your Gaussian process, f in this case, can be represented in the following form in terms of the eigenfunctions of the covariance function. So what do I mean by that? How do you have eigenvalues of a function or eigenfunctions of a function? Well, if you, in the theoretical sense, you have this associated integral operator where you integrate it against some function. In the discrete case, it's just a matrix, so it's going to have eigenfunctions. Okay, it's also going to have eigenvalues. So they show up in the formula here. And what this says is that you take a weighted combination of these eigenfunctions weighted according to the eigenvectors or the eigenvalues, and you also add in this randomness. where these are all IID Gaussians, these psi-i's. Okay. So this is maybe a little tricky to prove. You have to just, or at least most generally, it can be a kind of a difficult analysis problem in some ways, but in a discrete setting, this is much simpler. Okay, so if you have some sort of covariance matrix, it's going to be symmetric, positive, semi-definite. You diagonalize it, and then you just apply standard properties of multivariate Gaussians. So one orthogonal matrix is going to do nothing against the IID Gaussians. The other one's going to stretch everything out, and then the other one's going to give you the eigenvectors that are in this formula. Okay, so this is fairly easy to prove. It's just a discrete version of this. Okay, so where are we going with this? Well, one thing we still have to do, remember, is to pick a particular covariance function. And so what this tells us is that if we pick the covariance function to be the heat kernel, and these eigenfunctions here of our covariance function, an eigenfunction of the heat kernel that we've already talked about, then the Gaussian process embeddings, and you use the exact same eigenpairs as diffusion maps, just in a different way. Okay, and so it allows us to compare the Gaussian process embeddings to the diffusion maps in a very somewhat straightforward way. And it turns out to be pretty much the best thing imaginable for what you get out of this. Okay, so if you construct these Gaussian process embeddings and you look at the distance between 2 points in the embedding, that's this expression here. Well, these are all independent realizations, and we normalize. So that's just equal to the kind of expected distance for one realization of the Gaussian process, which is our canonical metric for the Gaussian process. Okay, so that's one object here. That turns out to be equal to the diffusion distance that we get by taking this covariance function to be the kernel for our diffusion maps. Okay. So canonical metric here, diffusion distance here. You have to take it at time equals 1/2 because there's the whole square root thing we talked about, but these are effectively the same thing. Prove this. Well, it's yeah, okay. So we got the process embeddings. What they do is they approximate the diffusion distance. Okay, you're not going to get the expected value all the time, but you embed in high enough dimensions, you'll get close. And yeah, the diffusion maps was an approximation anyway. So this is still we've shown something significant. Okay, so how do we prove this? Well, if you just take the distance, just subtract f of x from f of y over here before you square, you just have two linear expressions. You can factor out the sum, the ID values, then you just get the difference in the eigenvectors. When you square, you just have to write the same thing again twice, except you have an I and a j, which could be different. Then you realize, okay, this psi I and psi j, we're taking expectation. It's going to be 0 if I is not equal to j. And so you just you just go back to having I equal j everywhere and squaring everything, essentially. These have expectation 1, and that's exactly the diffusion distance. And that's it. Okay. Now, if you don't like that, if you don't like the Karhunen Loève expansion proof, you can do this in a discrete case. So remember, the pseudometric distance was given by the L2 norm distance between the rows. And then diffusion distance also had an L2 norm expression here. And so if you have the heat kernel and the stationary distribution is 1, then this is just going to be L2 distance, and they're the exact same thing. So have an integral over x, you just have a sum over however many finite positions in your matrix there are. Okay, I see a question, so I'll pause here. Difference. So the question is, what happens if you replace the eigenvectors with the different ONB? So what does ONB stand for?
Orthonormal basis.
Orthonormal basis. Okay, thank you. Okay, so slide 21, that was this here. Yeah, so if you Okay, so let's see. So if you go back here and you just define your own Gaussian process with a different orthonormal basis here of eigenfunctions or eigenvectors, and you plug it in, then you will get on this side a pseudometric corresponding to whichever symmetric positive definite matrix has those eigenvectors with those eigenvalues. You can just start with the orthogonal matrices and diagonal matrices multiplied out, whatever that is. And then over here, you'll still get the diffusion distance corresponding to whatever that matrix is. So yeah, we didn't really use any special properties of these eigenvectors or eigenfunctions. Yeah, in this proposition, yeah, this C is very general. Okay, so you can approximate distances like that. You can also approximate the Riemannian metric in a sense. So if you think about a point X and you think about two kind of tangent vectors at the point X, maybe one is going the direction of Y and one's going the direction of Z, you can run the same sort of argument and you get an approximation of that as well. So I don't want to say too much more about that, but just to say that this doesn't just approximate distances, or it'll also approximate angles. Okay, so all right, so we've shown so far that these Gaussian process embeddings approximate the diffusion distance, and that's great. But how fast? Well, if you fix a particular pair of points, and you look at how fast the distance in the embedding converges to the diffusion distance between those points, well, you can use your standard tools of central limit theorem, Chebyshev's inequality, whatever you want. You're just taking different independent copies of the same random variable and summing them and averaging them. So you get something very nice. You basically get that it converges like 1 over square root of k. And that's great, but when you're doing an embedding, you don't just want to have 2 points converge. You care about the worst case scenario. You don't want some sort of weird self intersections. You don't want 2 points that are very far apart to end up being very close to each other, even if everything else behaves very nicely. And so we showed something as well about the worst case scenario. Okay, so what does this theorem say? So this is the diffusion distance here that we're aiming for, or the pseudometric. And this is the straight line distance in the embedding. Okay. So what we're looking at now is what that error is, how far off it is, and we're looking at the worst case scenario over all possible pairs in our original index set. So what we can show is that the expected value of that is controlled by this expression over here. Okay, so it's made like a little bit of a mess if you're not familiar with Dudley's inequality. Dudley's inequality tells you in general how to bound the worst case scenario of some sort of Gaussian process or a more general random process. And it has expressions that look like this. So what are these? So over here we have the diameter of our space with respect to this distance that we're trying to approximate. We have the square root of 1 over square root of k that I promised. We also have this integral, which basically represents, well, before I do the integral, we have these covering numbers here. So the covering number of the metric space is the smallest number of balls of radius epsilon needed to cover the space T with the distance dc. So as you go to smaller scales, this is going to get higher and higher. And this is the kind of result that you tend to get when you use Dudley's inequality. So anyway, I won't try to explain Dudley's inequality in too much detail, but so real everything great, you probably see how this would be applicable. If not, the main point is that we're able to bound all of these errors simultaneously in a nice way.
Quick question is it not the square root of the log in the integral?
Yes, okay, so so typically in Dudley's inequality, if you have a Gaussian process, you have the square root here, the square root of the log. What happens here is, so these h's are themselves formed out of Gaussian processes, and then when we square them, we get something which ends up being sub-exponential, and this ends up, so we had to apply sub-exponential version, which just doesn't have the square root when you reverse it. Maybe you can get the square root back somehow, but yeah, we weren't trying to get necessarily the perfect version, just something that proves the point of you can do this and get something good.
Great, thanks.
Okay, so there's something that I've been conveniently ignoring so far, which is that if you have a covariance function or covariance matrix, it has to be symmetric. If you have a diffusion process or Markov chain, that has to be row stochastic. And just because you're one doesn't mean you're the other. Okay, so I've kind of been throwing these terms around, but we're in luck because the heat kernel, at least in theory on a manifold, is going to be bistochastic. Okay, but if we're actually going to compare random embeddings to diffusion maps, as we're going to, we want to see how they compare an approximating diffusion distance. We're going to have to be very careful about how we compare. Okay, so we're going to do, so here's one option. There's actually a somewhat common symmetric version of diffusion maps. So here before we row normalize to make a Markov chain, you can also do this kind of symmetric normalization. Okay, so you no longer have at least in general, you no longer have a Markov chain. Your top eigenvector is the square root of this kind of density term. But you do get this nice little expression for the diffusion distance. Okay, and this is something we can use. We can just say let's do diffusion maps of this. It's not going to have exactly the same properties, but it's a nice symmetric kernel, and it'll have a diffusion distance, and that's great. There's another thing you can do, which is you can do a bistochastic normalization. Okay, so what it says is you start off with your symmetric kernel, and you want to find, this isn't the same d as the one above. It's not the degree or anything. Just some arbitrary function that we haven't found yet, which you divide by in this way, and you choose it such that this is now bistochastic. Okay. And so if you use, it's a theorem of Sinkhorn and I believe Knapp that such a d of x exists, and there's a Sinkhorn iteration algorithm which tells you how to do that. Okay, so you can also bistochastic normalize, so you get something which is symmetric and a Markov chain. All right. So this gives us a very nice comparison point. Okay. So let's go on to some experiments. So yeah, so we want to compare the two. They're both the Gaussian process embeddings and the diffusion maps embeddings. And what we'd like to do is come with a fair comparison. So we're going to take these two heat kernels, these two symmetric kernels that we had on the prior slide, and we're going to use them both for diffusion maps and random embeddings simultaneously. So how does that work? Okay, so we have some data set. We're going to pick a manifold or some other generative process. We're going to sample n number of points. We're going to construct this sort of symmetric matrix to work with. And then we're going to compute both embeddings. That's not too hard. What we need to do then is compare the two embeddings. We need to measure success in some way. Okay, so what can go wrong with an embedding? Well, you can take 2 points and which are a certain distance apart, you can send them very, very far apart, or you can send them very, very, very near. So what this, the numerator is here is the maximum stretch of any 2 points under the embedding. So here f is now the embedding. In the denominator, we have the minimum amount of stretch. So if you have 2 points which come very, very close, that they'll attain this value. And then we take the ratio, so the maximum stretch divided by the minimum stretch. This is kind of like the bi-Lipschitz constant, if you're familiar with that, except we want to have the property that if all the distances multiplied by 10 exactly, we still say that's a good embedding. We only care about things up to the scale. Okay, so what we're going to do is we're going to take this d here to be the diffusion distance, since that's what we care about. That's the purpose of this, not necessarily recovering the original Euclidean distance. So we will check in with that as well. And then we're going to run this over and over again. So we're going to compare across multiple trials. So that's important for two reasons. One, if you sample differently from your manifold, then the algorithms can run differently. Two, the Gaussian process embeddings, you're going to have different realizations of the Gaussian process each time. And so even just for that, you have to run it over and over again and see what your average behavior it is if you want to experimentally figure out what happens in general. Okay. So we're going to do it over multiple trials. We're also going to vary over the embedding dimension. Okay, so here's the result for a very simple case. So we take the circle just in the plane, and we're going to embed it into dimensions 2, 3, 4, 5, and so on up to 8. This may sound a little silly, but we take something that's already in 2 dimensions and embed it into 4 dimensions and see how well that works. The reason is that what we may actually have is, let's say, a collection of images where they are the same object, but the object has been rotated a bunch of different times around some axis. And so each of those images is going to correspond to some parameter theta, which is an angle in the circle. And if 2 thetas are close and 2 images are going to be close, and you put together these affinity matrices, you're going to get the same thing. So this is just kind of, this is still important to figure out if what happens with this, if you care about embedding those collections of images. We just pick something that's easier to code and easier to be sure actually is that. Okay, so what happens? All right, so the diffusion maps is in blue, and it has very low L values, which is good because it means that the maximum stretch and the minimum stretch are very close. The Gaussian process embeddings are in red, and they aren't quite as good. Okay, they're especially bad in dimension 2. Okay, so I spent all this time talking about this new method for embedding, and I hopefully talked it up a certain amount. And now I show you the first result, and it doesn't seem to work. But there's a very good reason for that. And if we go into that, we'll see how to make it actually work. So let's say you take a circle and you randomly embed it in the plane, some closed curve. Well, it can self-intersect. It can look like this. Okay. And so these 2 points here are going to start off very far away and then very, very close in the embedding, and that's bad. The reason we measured this value L is because we wanted to detect self-intersections like this. This is the problem. Very large L says, okay, we shouldn't do this one. But okay, that's a problem. But let's say you go into 3 dimensions. Well, if you take a random function that varies a certain amount, it is with high probability going to now separate these 2 points along the next axis in the embedding. And so you're almost surely not going to have self-intersection. And that's consistent with what we were saying earlier about these being almost surely embeddings, right? So we have dimension 1, as long as you embed dimension 3, you're going to be good. And if you go back here, you can see on the chart 2 is way worse than the other ones. 3 is, it's okay. It's not too bad. Okay, now how about diffusion maps? Like, that's also doing really good. How are we ever going to beat that? Well, this was a nice perfect example where you have sine and cosine. These are top 2 non-trivial eigenfunctions. And so you're just getting a nice, beautiful circle out of the embedding. And there's no problems there. Diffusion maps is still very useful. Okay. So what we're going to do now is we're going to construct an example where the Gaussian process embedding is going to be much better. So here we're going to take a torus, so a circle across the circle, but we're going to scale the second copy of the circle by some value r. Okay, say 10. We're going to stretch it out. Okay, and we're going to embed in R4. Here's a formula for the embedding. This is very easy to analyze. We can find the eigenfunctions of the heat kernel. It's just because it's the product of these 2 sets. The eigenfunctions are going to be the products of the eigenfunctions on the 2 sets. So for the first copy of S1, we're going to have cosine of x for x is whatever point we have in S1. For the copy of RS1, then we're going to be able to go to lower frequencies to stretch out our sines and cosines along a bigger circle. So we have to divide by r here. And then we go through, we look at all the eigenvalues, And we see at the top non-trivial eigenfunctions, ones with the lowest values, or also the lowest non-trivial eigenfunctions, so the plus, if you want to think about it that way, they end up being these ones. It takes a while for the eigenfunctions to see the x variable. Okay. And so if you use diffusion maps, or similarly a spectral embedding in this case, and you try to embed this stretched torus, you're going to get a bunch of eigenfunctions which separate everything in the first copy, or sorry, on the second copy, and it's going to treat everything in the first copy as noise. That's not all bad. If the first coordinates here were noise, you would want to collapse them. That can be very useful sometimes when you want to denoise your data. But if you sample enough points from this torus, where you can tell, or at least you should be able to tell, that there's some sort of clear structure to these first two coordinates, you don't want to get rid of them like this. Okay, so what happens here? So here, the Gaussian process embeddings in red do much better, and the diffusion map embeddings take a while to catch up and still never really make it, at least up to dimension 12 even. So it's what we expect to happen in theory. Okay, so a couple comments about this. There's two blue ones now. So the dark blue corresponds here. The S is for symmetric kernel. The B is for bistochastic. In most cases, they were the same. If they were ever different, then we display them. So here it looks like the bistochastic version is doing worse. The theory says it's supposed to do poorly, so it's not. Don't be too judgmental of the method. Okay. Also, if we wanted to make this even more extreme in favor of the Gaussian process embeddings, we could have replaced 3.5 with the 10, and it would have looked way, way worse. But this at least shows you that diffusion maps does catch up at a time that you might expect. Okay, where it does look way worse is in a particular embedding of the Klein model we used. Here there's a clear gap. This is orders of magnitude better for the Gaussian process embeddings than for diffusion maps. Okay, so that was the first setting where we've seen that, if you have these different structures and different scales in your data, then Gaussian process embeddings can do a good job preserving some of the smaller scale structure instead of tossing it. Okay. Actually, if you think about the Karhunen-Loève expansion, and if you go back to that, we have all the eigenvectors in there, not just the top one. So that's one way you kind of see that might happen. Okay, so let's go on to another application where the Gaussian process embeddings are going to end up working fairly well. Okay, so let's take we're going to take a 4-dimensional rectangular prism. It's going to have varying side lengths, 1, 2, 3, and 4. Just take something semi-arbitrary, and we're going to put a Gaussian point cloud at each of the vertices. Okay, so the covariance is going to be 0.01 times the identity matrix. So means the standard deviation in each direction is really 0.1. You sample 10 points from there, you get some that are 0.2, maybe 0.3 away. They could be close to other clusters, but probably not. These should be clear clusters, just little bit of variance in there. Okay, so what's going to happen when we try to when we run the same experiments? We compare the distance of the embedding to the actual diffusion distance. This is what happens. This is a total disaster for the diffusion maps. And the Gaussian process embeddings are way down here, where everything is within order of magnitude of what you want it to be. Okay. And you might say, okay, the diffusion distance, is that really what we're looking for here? You can try to go with the Euclidean distance, and you get a similar thing. Okay, it's still not great here, but it's still significantly better than the diffusion maps. Okay. So what does this look like? What is actually going on? Well, if you run the diffusion maps on these point clouds, you get something like this. You have eigenfunctions, which are able to sort them into 3 groups, but there's not really a whole lot of sorting within each group. And if there is, it's at such of a small scale, you can't even see it on this big picture. It looks like there's 3 clusters. Over here, we have 3 instances of the Gaussian process embeddings implied to this data set. And what you can see is that, so these are all colored according to the original cluster. You can see that they're pretty well preserved. Right? It's not perfect, right? So over here, there's this brown dot, which is almost part of the screen cluster. but it's doing a much better job. And there's 16 of them we're trying to fit into R2. This is a very difficult task. And to get anything, that looks decent, I think we should be happy with. Okay. So a quick pause just for kind of general discussion. A lot of times people will use these sort of embedding tools for clustering, right? You take your data in very high dimensions, your clustering algorithm runs really slowly there. You pop it down to R2 or R3, you cluster it there. And what you hope is that the clusters that you have in your embedding are going to correspond to the clusters that you had originally. And so I would like you just to think about at some point in the future, if you do this, how confident are you in that assumption? Okay. So it may depend a lot on the technique. And even with good techniques, you can still run into problems. So, okay. So another case where our method is worked well is with outliers. So here we have a bunch of points in the circle and then 2 points that are off of it. What happens in this graph? So our embeddings do better for embedding in R2 and R3, way better than diffusion maps, and then diffusion maps catches up and surpasses them. Why is that? Well, if you diffusion maps ends up wasting 2 of its eigenvectors on the outliers. Okay, just on showing that those are in kind of separate clusters, and that takes a while to show the other structures. So this is diffusion maps applied to S1 of the outliers. You have the whole circle show up here, outliers over here. Zoom in the circle, kind of preserve the structure, but it's a little messed up. Okay, you do the Gaussian process embeddings, and you get something a little better. You get an embedding of the circle, which is still kind of on the scale of the distance between the circle and the outliers. You can also take your scale for the affinity matrices to be a little bit smaller, and you get something even better than this. But this just shows you another thing can happen. Okay. Couple more little things here. I think we're getting close to time, so I'll try to wrap this up. Okay, so this algorithm works by sketching a particular heat kernel. You can sketch with IAD Gaussians. You can also sketch with plus or minus ones with symmetric renewing variables. And so what this proposition here says is just that the distances or the angles that you have with this embedding, the expectation is still exactly what you would hope for in the prior case. Like we really didn't use any special properties of Gaussians in proving this result before. Okay. They also just have to be pairwise independent. You don't even need full independence here, which is nice. Okay. We did some experiments in there, and we get very, very similar things. Another thing, so diffusion maps has this natural kind of multi-scale analysis. So you have a diffusion process, and the diffusion process at a short time is going to look very different from the diffusion process over a long time. Okay, and that's very important. But at least from the perspective of the embedding, all that happens is, well, you get the same eigenfunctions. It's just the eigenvalues change, and so you're just reweighing each coordinate in your embedding a different amount. The fundamental structure is kind of it stays the same, stretches in a kind of funky way. For the Gaussian process embeddings, you have this multi-scale analysis. You have different scales, different powers of the heat kernel, but it's very non-trivial because all the eigenvalues and eigenvectors get jumbled together. Okay, so you take very, very small times, all these eigenvalues go to 1. So you just have a totally random vector. You get nonsense. If t goes to infinity, you're basically going to have something that behaves like the top eigenvector. And so you're also going to have nonsense, but in a very different way. So we ran some experiments that show the multi-scale analysis. So over here, if you take very low scales of the circle, you're going to get bad news for the Gaussian process embeddings. Over here, bad news. In the middle, not too bad. Diffusion maps is more constant. I think this is more just kind of like maybe not numerical error, but just kind of not quite as important over here. Same thing happens for the stretch torus, where it's very good at these good scales, not so good at the extreme ends. Yeah, so that's it. Thank you for your attention, and yeah.
Great. Thanks a lot for an excellent talk. I will stop the recording here and then open up the floor to questions.